Good afternoon, everybody. Thank you so much for joining us for another session of EI Live for K-12 students and educators, brought to you by the Institute at Columbia University. My name is Cassie, and I'm the Director of the Office of Education and Outreach, and a big part of my job is to bring our scientific research to different audiences. For those of you who aren't familiar with the Earth Institute, our core mission is to foster a greater understanding of the science behind climate change and sustainability and the climate crisis, and what we as global citizens can do. Experts that make up the Earth Institute include economists, specialists in public health, earth scientists, and business and policy experts. And the Institute is actually made up of more than 24 or so research centers and several hundred people who collaborate across many different disciplines and schools at Columbia University. So what we're hoping to do with these EI Live K-12 sessions is to introduce you to our interdisciplinary work through our experts. We're going to have sessions until the end of June, and so if you'd like more information on that, please email me directly. So today, we're very lucky. We're going to hear from Kyle Fitch and Anne Friedland. Kyle is a PhD candidate in the Department of Atmospheric Sciences at the University of Utah, and Anne is an adjunct research scientist at the Center for Climate Systems Research at the Earth Institute. They're going to show us just how much we can learn from the shape of snowflakes today. Everything from how we can expect the planet to warm to how much snow we can expect from an approaching storm. So as a reminder, we're going to be using the Q&A box today for questions for our presenters, as well as to answer some of our presenters' questions for you. We'll be monitoring the Q&A box throughout, so feel free to type in any questions as we go through the presentation, and we'll leave plenty of time at the end of the presentation to address all of your questions. If once the session is done, what we'll do is share a link with everybody registered for the event so that you can access the recording later on when it's posted to YouTube. And this video will also be archived on the EI Live K-12 site. So please email me directly if you're having any technical difficulties. And without further ado, here's Kyle and Anne.
Hi. So I'll start with a few slides. Does that sound good, Kyle? So my name is Anne Friedland, and I work at the NASA Goddard Institute for Space Studies in New York City. And my topic of research is cloud physics. And as we can see from the image on the left, the Earth is always partly covered by clouds. And what's less obvious from the picture is that some of these cloud particles are made of liquid, drops, and others are ice particles, for instance, snowflakes. Clouds reflect the sunlight's radiation, and we can see that by the brightness in the white appearance of some of these where the clouds are in the bottom part of the image. When they're very thin, they also preferentially hold in warmth. It's a little known fact that Kyle will talk to you about later, that most raindrops are actually melted ice crystals that have formed higher in the atmosphere where it's colder. So a crystal's morphology, or its shape simply, determines in part how fast it falls. And this image on the left was taken by the Apollo 17 crew on the way to the moon. And NASA is probably best known for its manned spaceflight missions. And this was the sixth and last human mission to the moon. But NASA also runs the Earth observing satellites. Next slide, please. So satellites are looking back down at Earth, and here's an example of a cirrus cloud that is sampled that we're seeing from different directions. On the left is a geostationary satellite image. This is a satellite that is in a fixed position, that it's able to stay in that position because it's about 1/10 of the way to the moon. And looking down, we're seeing Oklahoma. This black dot on the left is what we call a supersite, observing clouds from the surface. And the middle panel shows a radar looking upward. And the little red dot on the right shows the time period when the satellite image on the left was taken. And we can see that at this time, the reflectivity in the upper middle panel, I'll come back to radar in a moment, but this instrument is emitting radiation that is then being scattered back to it. And we can see on the left that a height of 10 to 12 kilometers is about where this cloud deck is, which we can't see directly from this satellite image. On the right, at the same time, an aircraft was sampling this particular cloud deck, and we can see the shapes of the ice crystals, which I think it's a little unexpected. We call this form bullet rosettes, and depending on the temperature and the water vapor mixing ratio in the atmosphere, these crystals form different shapes, and some of them tangle together as they fall at slightly different rates, and we can see that on the bottom right. Next slide, please. So my institute is responsible for building a climate model, which is for forecasting climate of our Earth. And for this, we need to represent all of these clouds around the Earth. And I'm showing here in these two panels the frequency of shallow clouds everywhere on Earth. And on the top and the bottom, the north and south poles, we see a red tone, which indicates more than 70% of the Earth there is covered by clouds. And these clouds, because it's so cold, are primarily ice-containing clouds. And how much ice they contain affects projections of how warm the poles will be relative to other parts of the world in future climates. And these are just two versions of our model, and I won't say more about that. Next slide, please. So we need to approximate the ice crystal sizes in order to represent clouds in those climate model simulations, and that's part of my job. Ice crystal shape also affects weather radar returns, and I'm showing just the range of our weather radar that covers where I live in New York City, and it's on Long Island here. And this radar is emitting electromagnetic radiation, not vertically pointing like the last image I showed earlier, but now scanning up and down and around, and maybe you've seen these images on the evening television, for instance. And that ice particle shape also affects how weather radar scattering occurs. Namely, we get more backscatter from larger or denser ice crystals like hail. And a lack of systematic knowledge of particle shape currently limits our ability to interpret what radars see, for instance, for snowfall forecasts. Next slide, please. So I will turn now to Kyle, and I'll just say thanks for your help in getting more systematic knowledge of ice crystal shape.
All right, thanks, Anne and Cassie. So that was a nice introduction by Anne talking about some of the things that NASA does and how the snowflake shape relates to that. What I'm going to do is just start out talking about how clouds form, and then I'll get into how we get to the different shapes that we see in snowflakes. So first of all, what is a cloud? Well, we need three basic ingredients to form a cloud. The first one is water vapor. And if you think about the three basic states of matter that you've probably come across in school, for water, for example, we have the solid state, ice, we have liquid water, of course, and then we have the gas state, which is called water vapor. So if you think of a boiling pot of water, the water that's escaping from the liquid is becoming vapor. So we need that gas form of water, we need that water vapor. And then we also need these tiny particles called nuclei. And you can think of these as just seed particles for cloud droplets. And on the right-hand side of this figure here, I have the different sizes. So if you see this large semicircle, that's a raindrop. So if we zoomed in and enlarge the size of a raindrop, that's approximately the size that it would be. And over here we have a drizzle drop. That's basically a small raindrop. And then up top we have a cloud drop. And so that's how much smaller a cloud droplet is compared to a raindrop. And then lastly, on the right-hand side, we have a nuclei, and that's the seed particle. And you can think of that as just tiny dust particles that are in the air. And so you have to have these little particles in order to get these cloud droplets to form, and then they'll start growing once that happens. But the last thing you need for that to happen is cooling. So you have to have some sort of cooling process. And the most common one is shown here, where you see the rising air. So as air rises, it expands. And when it expands, it also cools down. So that's where you get the cooling from. So you have the tiny nuclei seed particles, and the water vapor attaches onto those, starts to grow into a cloud droplet, and then those droplets get bigger and bigger, and I'll talk about that. And if they get big enough, they'll fall out of the cloud, and they'll fall out as rain if it's warm enough. But the clouds we're talking about today are cold clouds. So if the temperature is below the freezing point, we can have clouds that are either entirely ice particles, or they're a mix of ice and liquid droplets. And that's something important I want to point out here, is that even though it's well below the freezing temperature, we still have, oftentimes we have a lot of liquid in the cloud still. So these liquid droplets are in the cloud, and they don't freeze even though the temperature is well below freezing. But if something happens, they can freeze very rapidly, and I'll talk more about that. So this is kind of an interesting picture that I wanted to discuss. You may have seen this in the sky before, or you may have seen pictures. And so I want to just look at this and think about what might have happened. Well, the thing that happened is prior to this picture, that cloud deck was entirely liquid, and that liquid was super cooled. So it was below the freezing temperature, but it wasn't frozen yet. And so you may have seen this demonstration before, where you have a bottle of liquid water that's below the freezing temperature. So you can put a bottle of water in your freezer. You can try this at home, and it will drop below the freezing temperature, but as long as you don't disturb it, it won't freeze yet. And so what the person is doing here is slamming it on the table, and that disturbance causes the entire bottle of water to freeze almost instantaneously. And that's pretty much what's happened here. Is there's some disturbance. In this case, it's usually an aircraft, so an airplane probably flew through the cloud deck, and that disturbs the liquid droplets, and then they freeze really quickly. And there's also some blue sky around the ice particles, and that's because the ice particles grow while the liquid droplets evaporate. And so you get this kind of clearing sky around this group of ice particles. So the next time you see this, that's what's happened. And this is called a fall streak hole, or a hole punch cloud. And so you get this kind of domino effect where a few ice crystals freeze, and then the whole entire area becomes frozen. So once you form ice crystals in a cold cloud, the way that they grow first is by what we call vapor diffusion, which just means that you have an ice crystal, and the water vapor molecules that I talked about, so that, again, that's the water in the gas state. Those water vapor molecules attach themselves to this crystal, and it grows just like this. And something you might notice is this particular ice crystal has 6 points, and kind of in the shape of a six-pointed star. And all ice crystals have this basic six-sided or six-pointed shape of a hexagon. So the basic shape is always a hexagon, but how it grows, exactly how it grows, as Anne mentioned earlier, depends on the combination of temperature and humidity. And humidity is just how much water vapor is there in the cloud. So temperature is along the bottom of this figure here, and as you go from left to right, it gets colder. And humidity is on the up and down axis here, and as you go up, that's an increase in humidity. And one thing you'll notice is at the bottom, we have the basic hexagon shapes. Some are called plates, and some are called columns, and that's noted at the top here. So you have pretty basic shapes when it's lower humidity, but when you have a lot of humidity, you can get these more complicated kind of star-shaped, or we call these dendrites or stellar plates. You get these more complicated shapes when you have a lot of humidity. And then when your temperature changes, in certain temperature ranges, you might get more plate type shapes where it's kind of a flat, broad shape, kind of like a dinner plate, but in the shape of a hexagon. And then as you get colder, you might get more column type shapes, which are just long cylinder type shapes. And then as you get colder still, you go back to the plate shapes. And then even colder than that, you get the column shapes again. So exactly what shape you get really depends on, exactly what shape of ice crystal, I should say, depends on the temperature and humidity. But the two basic shapes that, if you remember anything from this, the two basic types of shapes that I want you to remember are plates and columns. And that's what's shown here. So again, the plate is just a flat, broad, hexagon type shape. And then the column is a long cylinder type shape, but still in the shape of a hexagon overall, so still six-sided. And these are basically, they're both hexagons. One has just grown outward and maintained its flatness, and the other one has grown lengthwise into a column. So you can see here lots of different types of shapes. These are pictures of ice crystals that were grown and photographed by a man named Kenneth Liebricht, and he takes some really interesting photographs of these ice crystals. So we can see a lot of different shapes here. We can see plates and columns, and we can also see combinations of those in the middle here, where you have kind of a column with a plate on the end of it. Those are called capped columns. And then again, you get the dendrite star, kind of six-sided star shape when you have higher humidity. So first question, and we'll do this through the poll, is what are the two main types of ice crystal shapes, also known as habits? So you should see a poll questionnaire pop up on your screen, and just choose whatever you think is the best answer.
All right, Kyle. So the results are coming in. It seems like most people have selected D, plates and columns.
Okay, good.
We have two answers for A, for hexagons and circles, and one answer for C, aerosols and nuclei. But the vast majority of individuals have responded plates and columns.
Okay, great. Yeah, I did try to trick you a little bit because we have talked about those other things. But yeah, the two basic shapes are plates and columns, so good job. Okay, we'll move on to the next slide here. So after these ice crystals grow, what we want to know is how do they get even bigger and eventually fall out of the cloud? And that happens through collisions. So let me see if I can move this. I don't know if you can see that, but so through collisions, the ice crystals grow even larger and eventually large enough to fall out of the cloud as snowflakes. And just like there's two basic shapes of ice crystals, there's two basic ways that these can collide. The first is with an ice crystal colliding with another ice crystal, and then they stick together, and we call that aggregation. And the resulting snowflake is called an aggregate. An aggregate just means a cluster, so it's just a group or a cluster of ice crystals stuck together. And then the second way is if we have both ice and liquid in the cloud, the ice crystals can collide with the liquid droplets. And remember, the temperature is below freezing, so as soon as they make contact, the liquid droplets freeze almost instantaneously onto the ice crystal. And usually the liquid droplets are much smaller, So you get this kind of roughened texture on the ice crystal. It looks kind of bumpy because basically that is what you have on the ice crystal. You have these little bumps of droplets that have frozen onto the surface. So aggregation and riming are the two basic types of collisions. So this is an example of an aggregate where we have a bunch of dendrite crystals stuck together. And this is showing some riming where we have an ice crystal that has collected some liquid droplets that have frozen onto the surface. This 1 through 5 is showing the progression. So you start out with just a regular ice crystal, and then you start collecting these liquid droplets more and more until eventually you start to get this kind of ball-shaped, what we call a grapple, and that's written right here, G-R-A-U-P-E-L, grapple. And a grapple is really just a small hail particle. So if you get a really severe thunderstorm, then you get these really strong upward motions. We call them updrafts. And these grapple particles can grow and grow, and they can keep on growing in these really strong upward motions until they get really heavy and fall out of the cloud as hail. So grapple is really just small hail where an ice crystal has collected liquid droplets. And then the other thing I wanted to show, and Anne mentioned this, is that almost all rain that we see, especially here in the United States and near the poles, is started out as ice. So all of these ice crystals we've talked about, if it's warm enough below the cloud, they can melt and turn into rain. And so most of the rain we see was once an ice crystal or a snowflake. And the only exception really is in the tropics where it's too warm all the time. So rain is always rain. So the second question I wanted to ask you is, what are the two ways that ice particles grow through collisions? So again, just choose the answer that you think is best.
Okay, so the answers are starting to come in. We have most participants have selected B, rhyming and aggregation. 2 answers for temperature and humidity, and 1 for water vapor, diffusion, and nucleation.
Okay, great. Yeah. I threw some tricky answers in here because remember, temperature and humidity determine the shape of the ice crystal, but it's the collisions of aggregation and rhyming. That's how we actually grow into much bigger particles called snowflakes that eventually fall out of the cloud. Well, good job. Okay, so when we think about snowstorms and we think about those 2 different types of collisions we talked about, remember on the left-hand side, a grapple is what you get if you have enough rhyming, where you have the ice crystal colliding with liquid droplets. And remember, that's kind of small hail. And you may have seen this before. What it looks like is almost like a rain shower, except it's frozen. And so you get these little balls of ice that they tend to bounce off of your vehicle or off of the pavement. And that's much different than on the right-hand side, where we have these aggregates, which is again a bunch of ice crystals stuck together. And these can turn into really big, complicated shapes compared to the grapple, which are pretty round and usually pretty small and compact and very dense. So usually what you get is with a grapple shower, you don't get a lot of snow accumulation because it's pretty short-lived. And again, you get these kind of bouncy particles, but they don't last too long. But the really heavy snowfall comes from the scene on the right, where you get these really large aggregates that stick together. And when that starts to pile up on the ground, it can get really deep. And that's where you get the really deep kind of snow from. So that's why understanding the shape of snow is important for understanding how much snow accumulation you can get from a snowstorm. And again, Anne talked a little bit about radar. And so we use radar kind of in the short term, like in the hours and minutes as a storm is approaching to forecast what's going to happen. And so these are some different radar images with different shapes and sizes of snow, just to show you some examples. And then on the right-hand side, this bright red band here in the radar, this is another radar that's looking upward, like the one Ann showed first. And in this case, that bright red band is actually where the ice particles are starting to melt. So below that is actually rain, and that bright red band is actually where this melting is happening. So we talked about why it's important to know the shape for an approaching snowstorm, but another thing that Ann talked about was it's important to know the shape for our models, and whether that's trying to model the weather for the next day or the next week, or whether that's trying to model the climate, which is how the weather changes over a long period of time. So maybe 10 years from now, or even 50 years from now. And so we need to know these shapes, because if we look at this situation, this is a daytime situation. So let's say we have a cloud on the left-hand side that starts out, we have a cloud at 12 o'clock p.m., so noon, and we have some grapple falling out of it. And this cloud is reflecting the sunlight. It's absorbing and re-emitting the long wave radiation, which is, you may have heard of infrared radiation before. That's radiation that you can't see, unlike the sunlight. But clouds and the ground are always emitting this infrared radiation. And if the cloud is absorbing that and emitting it back towards the surface, then that's keeping the surface warm. And so if we have this grapple falling out of the cloud, that's these really dense particles. And so we're losing a lot of water for every minute that grapple is falling out of the cloud. And so if we're losing a lot of water over a short period of time, then eventually that cloud is going to disappear. And once it disappears, that sunlight is now reaching the surface completely, rather than being reflected back to space. And the ground surface radiation is being emitted all the way up to space, and the cloud is not absorbing and re-emitting that. But if we have aggregate type shapes, type snowflakes falling out of the cloud, we're not losing as much water in a period of time, say like a minute. So that cloud tends to last longer. And so say like a half an hour from now, that cloud is more likely to be around still. And so it's still reflecting energy back to space, and it's still trapping the heat near the surface. At nighttime, it looks a little different because we don't have the sunlight. So we just have the infrared radiation. And so if you have a cloud there, that cloud is, again, it's trapping the heat and it's keeping the surface warmer. But if we have grapple falling from it, it's probably going to disappear faster, and all of that heat is escaping to space. So then in that case, the surface is cooling off really quickly. But again, if we have the more complicated aggregate shapes, then that cloud is more likely to stick around and keep the surface warmer. So that's how we figure out how the temperature is going to change based on whether the cloud has different snowflake shapes falling out of it. So if we put that into our model and try to predict a long time from now what's going to happen based on the snowflake shape, that knowledge of the snowflake shape is really important. Okay, so now we're going to move into our demonstration. And so if you have the materials, go ahead and grab those now, which was 4 pieces of paper. And one of those pieces has the kind of hexagon and square pattern on it that you'll need. And you'll need some scissors and tape. And then as optional materials, I have listed some glue and some small styrofoam balls. And that's going to simulate our liquid droplets. But again, that's optional. So if you don't have that, no problem. And if you don't have any of the materials, you can always go to this link that I'm showing here. So I'll give you a minute to type that in. And if you go to that link, you can have the opportunity to take what I've just taught you and try to guess what the type of snowflake is. So you'll see some images from a snowflake camera of different types of snowflakes, and you can just make your best guess on this website of what type of snowflake it is. Okay.
So in the meantime, while we're getting, while Kyle is restarting the presentation, and I thank you for answering the questions. We have one that I know you've been answering in the Q&A box, but we have one that is now just coming in. So, Anne, do you want to see if we can answer this one live for Annie Lee? So, Anne, I think you're on mute. One sec.
Oops, sorry about that. Yes, thank you. Thank you. So the question is, living in a place that gets a lot of hail, Grapple to me is very different, much more of a styrofoam type of consistency versus a hard pellet of ice. That's true. So, so that what happens there is that some water basically gets incorporated. I'm sorry, air also gets incorporated. So small cloud droplets, when they freeze very quickly onto ice is falling through them, collecting small cloud droplets. And if they freeze, those droplets freeze very quickly. They're spherical, and so it's a lot like styrofoam in that there's little pockets of air in there. And so the particle is not as dense. And so that's exactly right. And sometimes both hail and grapple can get quite large. So I don't know if Leanne has seen some of that. It can be frightening sometimes.
Great, thank you. And we've had a lot of great questions from our audience that I see Anne has answered. Anne, do you want to
Sure.
yeah, want to expand or comment on any of those?
Yeah, one good question was, is there a height at which water droplets always stay in the ice form? And so this is actually a difficult question. So really, it's about temperature. So it's not so much a fixed height as a temperature. So in colder parts of the Earth, that temperature is closer to the surface. Is it, cold enough that you can form ice? And so my simplest answer for this is that ice doesn't melt unless you reach the melting temperature, which is 0 degrees Celsius. And actually, there's quite a wide range of temperature where crystals are present at the same time as droplets, and hence the rhyming that we just discussed with respect to grapple pellets. So I'll pass this back to Kyle.
Okay. And then if you can still see me, what you end up getting is we were working on cutting out the snowflake shapes. And if you tape a bunch of those together, that's a lot like an aggregate. And then if you cut out and tape the hexagon, the solid hexagon shape, you end up getting the kind of a rhymed looking crystal once you glue the styrofoam balls onto that. So the next video is just showing me doing a little experiment with those. So that's the one I'll move on to now. So what I'm doing here is I'm just dropping both. I've just aligned the videos so that the aggregate and the grapple, the rhymed crystal, are falling at the same time. And you might make a guess which one's going to fall faster. And so let's find out. So as you can see there, the grapple falls much faster because it's got that dense, compact shape compared to the grapple, which has a much larger surface area and a lot more complicated shape. It's a lot more spread out. So it's got a lot more air resistance as it falls. So it falls a lot more slowly. So that's something I want you to take away from why snowflake shapes matter. Well, they determine how fast snow falls out of the cloud, right? So that was the point of that. So just to summarize here, I showed you the two basic shapes of snowflakes, of ice crystals, which were plates and columns. And then we saw that they grow larger by colliding in two different ways, which was either aggregation and forming into a cluster, or by rhyming, which was colliding with the liquid droplets that then freeze onto the surface. And as Ann and I both pointed out, most raindrops were once ice crystals. And then as that little experiment showed right at the end there, the shape determines how fast these are falling out of the clouds, which in turn determines how long is cloud cover lasting. And if clouds dissipate, the energy balance changes, temperatures change, and depending on how much water falls out of the cloud in the form of snow, the water distribution can also change. So that's all I wanted to show you. I'll leave this page up here, and then I'll take any questions that you have.
Great, thanks, Kyle. And if you want to join us again, turn on your video. We've got two questions that I think Ann just answered one of them, and then we'll answer the other one live. And just a reminder to our audience, feel free to type in the questions that you have into the Q&A box. The remainder of the time that we have will be used for your questions. And this link, along with the materials that you'll need for the demo, along with a recording, will all be shared with you in a couple of days, actually within this week. So Kyle, can you see the Q&A box? And Ann?
No, but I think if I click on it, okay, yeah, I can now.
Yes.
Okay.
Yes, I can
Perfect.
see.
I'm gonna let you just take a look at that, and if we can answer these live.
So I'll read the last question, and maybe Kyle, maybe you want to take this one. What will happen if aggregation and rhyming happen at the same time?
Great question. Yeah, I'm glad you asked that, because that actually can happen anytime, and it's actually likely that you do get a combination of that. So because you have ice crystals and liquid droplets in the cloud together, when you have that mixed phase type of cloud, you can get collisions with liquid droplets, and you can get collisions with other ice crystals. So usually a lot of the particles that we see falling out of these clouds are not really if you have a lot of rhyming, you'll get a grapple for sure, but a lot of times we'll see these aggregates that are partially rhymed. So you can definitely have both happening within the same cloud, and usually that's what you see.
Great. And a second question we had is, let's see, actually, we just got another question. Well, I'll cover the global warming first. Does global warming cause more rhyming or aggregation? And perhaps we can both answer this one, Kyle. My first answer is that to first order at higher latitudes, near the poles, we'll see more liquid water clouds. And that would lead to more rhyming, generally speaking. So I don't know if you would, what do you think about aggregation?
Yeah, well, that's a question that has come up here in Utah, because Utah is famous for its snow for skiing. And for good skiing snow, you need the aggregates, because when they stick together on the ground, they make this nice fluffy type snow that's soft, and it's a good powder, as skiers call it. But one hypothesis, one guess that scientists make is similar to what Ann said. If you get more warming, then you would expect to have more liquid in the clouds. And so maybe you get less of this nice fluffy aggregate type snow, and you get more of the dense rhymed grapple type snow, which is not very good for skiing. Good
Yeah.
question.
So we have another good question. Teachers tend to call clouds and steam water vapor, I guess because they can be seen. So like you see a steam. Do you have a suggestion of another way to explain water vapor without misleading students?
Yeah, that's another good question, because when I was just looking for images that try to show what water vapor is, it's difficult because, yeah, you can't see it. But I guess the best way to think of it is just to think about how the molecules behave differently. So rather than looking at maybe like, if you look at some steam coming out of a teapot or something, that steam that you're seeing, those are the droplets that are large enough to see, so they're liquid. but again, yeah, you can't see the water vapor. So, but you know that because that's hot steam coming out of there, that liquid is turning into water vapor. So maybe one good way to think about it is to think about like after you've taken a hot shower and the bathroom is really steamy, you can almost feel the increased humidity, and that's just more water vapor in the air. It feels kind of heavy, just like a hot humid day feels kind of like the air is kind of thick. So I would say maybe it's easier to think about how it feels than what it looks like. But if you are trying to visualize it, then maybe focusing on the molecules and what they're doing, maybe that would help.
We
Yeah.
have a lot of we're getting a lot of questions, or I got an earlier question. I'm not sure I answered it very well. Can you explain more about how water can stay liquid even though it is below freezing? And I'll give you my quick answer, and then Kyle, I'm curious how you would answer that. So the way I think about this is that if you have a cloud droplet and you lift it up in the atmosphere, as Kyle mentioned, um, pressure is lower aloft, and air expands and it becomes cooler. So as that droplet cools and you go through the freezing temperature, the stable phase of that droplet is ice. And if it were to become ice, it would not melt again until it were brought back to that warmer melting temperature of 0 degrees Celsius or 32 degrees Fahrenheit. But it doesn't immediately freeze. And the reason for that is because it needs to go from a disordered state of liquid water to the ordered state of an ice crystal. And that actually requires a reduction in chaos or entropy. We call it entropy. And that requires an input of energy, or it can also, something that can lower that energy barrier is to introduce something that ice to that droplet. If it were to encounter an ice crystal at those temperatures colder than the melting temperature, it would immediately freeze. Or if it were to experience another surface like dust that looks a little bit like ice, that can also lower the energy barrier. But that droplet, if it were completely pure, will not spontaneously freeze until it reaches temperatures colder than -30 degrees Celsius. And how quickly it freezes, it'll be a random event within the droplet. So it's more likely to happen the bigger the droplet is. What do you think, Kyle?
Yeah, I think that's a great answer because there are so many different ways that it can happen, but any one of those ways you do need some kind of, that's why I kind of tried to summarize it as a disturbance, because you need some kind of like boost in energy, like Anne said, or you need some kind of new particle introduced that looks like the ice molecule that can initiate that freezing process for the molecules to sort of begin to rearrange themselves.
I like to say that none of the water molecules wants to become an ice crystal first.
Yeah. Yeah, and as you get to colder and colder temperatures, you're more and more likely to see that. But you can get, yeah, well into the -30-degree Celsius temperatures before that happens.
We have another question. Why is it called a cloud? Is there a specific reason for that? And I guess my answer would be a little bit philosophical because, for instance, when a cloud is touching the surface, we call it a fog. But it really is a cloud that's touching the surface. So I think it's a little bit arbitrary what we call a cloud and what we call precipitation particles. So they fall out of clouds, but really there's a whole continuum of sizes from the smallest particles that are not falling fast at all to the ones that are falling at significant speeds, meters per second from clouds. What do you think, Kyle?
Yeah, I kind of tend to want to give a philosophical answer. And this is an interesting question because I don't know. I mean, why is it called a cloud? I guess maybe you'd have to ask a etymologist, somebody who studies words, because I think maybe the base, wherever that word originates, probably means like a collection of like particles or something. But we often, scientists often debate, well, what is a cloud though? Because it kind of depends on what sensor you're using. Normally, we just think of a cloud as being something we can observe with our eyes. But if we're using a sensor from space that uses a different part of the electromagnetic spectrum that's not in the visible range, then what is a cloud becomes slightly different. So it's an interesting question that we actually still discuss quite a bit.
Great, lots of great questions here. So I'm going to, I'm just in case we run out of time. I think there's a few that are sort of similar, but there's this one question here: can the snowflake be any other shape than round after rhyming?
Yeah, good question. So yeah, I'd say that the spherical round shape is probably most common, but you can also, the other most common type is a cone, which I didn't show, but yeah, kind of based on the way that the particle falls, it can actually form more of a conical, more of a cone shape, where it's wider at one end, and so it kind of comes to a more of a point on the other end. And that's just kind of a matter of, as it falls, if it collects more on one end than the other, then it starts to take on more of that cone type shape. And then I've also heard of hexagonal grapple, but I haven't been able to find any images of those. I don't know about you, Anne.
Well, I study polar clouds quite frequently, and those clouds contain fantastical shapes. And because they form in clouds that are very close to that homogeneous freezing temperature, I won't go into too many details here, but the ice crystals will start to grow very rapidly, and so they grow into what we call chaotic shapes or florid shapes, and any little discontinuity will grow into a new a plate, for instance, if it's at the plate forming temperature that Kyle showed earlier, and we call those radiating plates. They'll just be plates growing out of one another, more like what you would see on a a rock crystal or something like that. And then additionally, you can form crystals that are very slender and long. We call these Shimizu crystals after the scientist, the Japanese scientist who discovered them. And these are, to my knowledge, only occur at polar latitudes.
Great, thank you both. The next question, is it also possible for liquid water to be in the range of latent heat and therefore not freeze because it is trapped between the state of solid and liquid?
Another really good question. So when we think about how hail grows, we have these two different regimes called dry growth and wet growth. And so, yeah, that's, you bring up latent heat. Well, as those phase changes occur, heat is released. So there's always some sort of balance um, between the heat being dissipated away from the hailstone and cooling. So it's really just depends on the balance of all that. And so if you can keep it below the melting point, then you stay in that dry growth regime and you just have ice. But you usually, what you see in a hailstone, and maybe you've seen like a cross section of a hailstone when they kind of cut it in half, and you see alternating layers, and usually they're alternating layers of dry and wet growth, where part of the time that the hailstone was growing just as ice collecting, and then the other part, well, I should say, the whole time you're rhyming, right? So that how quickly the rhymed droplets freeze onto the hailstone surface, that's all determined by that balance of heat flow, really. So sometimes the droplets kind of ooze in before they freeze completely, if it's a little warmer, and then if it's colder, then they'll tend to just freeze much quicker, and maybe there's more kind of pockets of air. If that, hopefully that answers your question.
I would love to suggest to people who are interested in these topics, from my agency, NASA, we have what we call the Global Precipitation Measurement Mission. And this is a constellation of satellites, including a big kind of mother satellite that's a radar. So it's actively pulsing, and and then a big constellation of other microwave radiometers, we call them, and they're sensing. And so there's a link on the announcement for this session where you can go to the web page and see information about that satellite mission, which is up now.
And we'll be sure to share that link in the follow-up email with everyone who's registered for the event. So we have another question. This one is about basically what's sleet in the context of everything sort of you've talked about. I think you've mentioned hail, ice, and snowflakes, but tell us about sleet.
Yeah, so we just talked about some kind of simple scenarios where you could have snowflakes melting after they fall out of the cloud and they turn into rain, but you can also have a situation where you have a cold layer, so you have a snowflake falling, and then it falls through a melting layer, melts into a raindrop, and then it falls into another cold layer. So you have a warm layer sandwiched between two cold layers, and so that raindrop refreezes, and so it looks different because it's become a raindrop and then it's frozen again. So it looks more transparent compared to like a grapple, for example. And then related to that is if that cold layer at the surface isn't very deep, then that raindrop can become super cooled, like we talked about. It can become super cooled again, and as soon as it makes contact with the surface, it freezes instantly, just like rhyming, and that's called freezing rain.
Great, thanks, Kyle. And here's a bit of a historical question. Before people knew what ice crystals were, what did they actually think it was?
Yeah, great historical question. Yeah, I don't know, Anne, you might know this better than I do, Anne.
Yeah, well, that's a great question, and I don't really know the answer to that. But as I mentioned in an earlier question along these lines, it wasn't until roughly the 1930s that people realized, and this were some scientists in Europe, Northern Europe, that most raindrops were actually melted ice crystals. And even later, and Kyle, I think a lot of scientists in our community don't often realize that what we call the warm rain process was not discovered until the 1940s, even later. So you can form rain just from collision coalescence of droplets. Not all rain forms on ice crystals. And first it was realized that most did and thought that all did, and it wasn't until another 10 years later, and it was actually wartime radars that sensed this what we call warm rain formation, and realized that not every raindrop actually does go through an ice phase. It's less common, but warm rain does occur. So before that, that's a good question. Maybe different people had different ideas about what was there. And what actually surprises me the most about cloud physics is how much we still don't know. So I see that in a long continuum.
Yeah, and that's one thing that makes cloud physics so interesting is that, yeah, like Anne said, there's just so much still that's so mysterious to us.
Definitely. Okay, so I'm going to wrap up with one more question. So for those of you that did have open questions, I just want to be respectful of people's time here. Kyle did kindly put up his email address, so if there's very specific questions that didn't get addressed, feel free to either send those questions to me, and I'll definitely pass them along to Anne and Kyle. But for the last question of today, let's go with, it feels warmer after a snow day, and the participant would like to know why.
Yeah, so it can kind of depend on whether clouds stick around after it snows. So let's say it snowed the day before, if those clouds were still sticking around overnight, then on that one slide I showed that clouds will trap the heat at the surface. So that's one way that it could feel warmer. Because otherwise you will get a lot of cooling overnight. So um, if you get a snow day followed by clearing overnight, that's usually, feels much colder the next day. But kind of just depends on how quickly high pressure builds in and what sort of clouds come in behind that. But yeah, you can also get, as the snow starts to melt, you can get different temperature influences from that. So yeah, I guess it kind of just depends on the situation. But I'd say clouds have the biggest influence.
Good answer.
Great. Well, thank you both. Any closing remarks from Anne and Kyle? A lot of great questions today from our audience.
So I guess I'll just jump in and say that, so this project came up because we actually needed help categorizing ice crystals visually. And so we thought, well, maybe we could hire an undergraduate, but we thought, well, maybe with something like Zooniverse, kids of all ages could learn about ice crystals and become interested in them at the same time as we get help categorizing them. So for all of you who want to spend time on here, this is not just a lesson plan. This actually helps us. Kyle?
Yeah, so if you do go to that Zooniverse link, especially if you think this is pretty interesting, I encourage you to go there. I think you'll see a lot of different pretty cool images of snowflakes that are pretty fun to classify. And my son has done it. He's going into 6th grade and he enjoys doing it. But yeah, so thank you for your help with that if you do decide to do that. And I really enjoyed your questions, and definitely don't hesitate to email me if you have more questions. And like Cassie said, we'll get the video up with the full demo. So if you want to do that at home, again, I apologize for that not working, but hopefully you enjoyed the video that followed where you saw the different fall speeds of the different snowflake shapes. So yeah, thank you for your time, everyone.
Great, thank you both. And just a quick plug for Kyle is actually doing another session next Monday, June 8th, from 2 to 3 p.m. Eastern Standard Time, where he's actually going to get into snowflake classification a little bit more. So that session is more geared towards students at the high school level and undergraduates. But if you enjoyed today's session, feel free to tune in for that. We'll also have a recording where he's going to talk mostly about how machine learning is actually being used to automatically classify images of snowflakes, and that should be very exciting. So thank you again, Anne and Kyle, so much for doing this. Thank you for our very active audience. We really appreciate your questions. And if you have any additional questions, feel free to get in touch, or if you want to know what other sessions are coming up in this series, and we'll be sure to send the videos and all the resources that Anne and Kyle have talked about with everyone who has signed up for today's session. So with that, I'm going to wrap up here, and thank you again to our presenters, and I hope everybody has a great rest of the day.
Thanks for hosting us.
Thank you.